Hey students, in this video we're going to cover cylindrical coordinates. Cylindrical coordinates are polar coordinates in 3 dimensions. So we're going to have a radius, r, an angle, theta, and now we're going to have this depth value, z. Kind of similar to the double integral we have where we have r, dr, d theta. Now we're just going to add a differential for z as well. Our angle, theta, and radius are always going to be determined by the region made in the xy plane and by the intersection of our surfaces of z. Um, Most of the time, this is relatively straightforward, if not just tedious for the algebra that we have to do, but analytically, it's all generally pretty direct. So, for our first example, we have this density function 5 minus z, and we want to integrate this region that over the region that's bounded by the xy plane, which is going to indicate first that here z equals 0, and the solid z equals 4 minus r squared. So remember, r squared is x squared plus y squared. So really, we've already converted z equals 4 minus x squared plus y squared. And we know that this is a paraboloid. So all the density means is that it's going to change depending where we are on the like internal in the surface. And so the mass isn't uniformly distributed. And so the mass of the object over this region is the result of this integral. The setup for this is pretty straightforward. So again, to find our radius value, we're going to set our two surfaces equal. And the intersection of those surfaces is that's the region that we're integrating over. So we have z equals 0, which is the xy plane, and z equals 4 minus r squared for the paraboloid. All we're saying is that 4 minus r squared equals 0, so 4 is equal to r squared, and plus and minus 2 are equal to the radius. For anything geometric, only a positive is going to really matter. So we know our radius is 2. So our limits for r are from 0 to 2. Our theta, as long as we're going around a circle, is always going to be 0 to 2 pi unless we indicate otherwise. And our limits for z are going to be from the plane up to the surface. So from 0 to 4 minus r squared. So our triple integral is going to be the integral from 0 to 2 pi, from 0 to 2, and from 0 to 4 minus r squared. And we're going to have 5 minus z. So 5 minus z, which is, so 5 minus z, r dz dr d theta. So the inner integral is going to give us 5 5z minus z squared over 2, evaluated from 0 to 4 minus r squared. And so this is just going to be algebra intensive, not difficult. We just have to do algebra well. So we're going to get 5 times 4 minus r squared minus 4 minus r squared divided by 2. And then when we substitute in 0, we actually get 5 times 0 minus 0 squared divided by 2, so just 0. So now here our work is going to be to simplify this. So we're going to get 20, 20 minus 5r squared, and then minus, so that's going to be 16 minus 8r squared plus r to the 4th, all divided by 2. And don't forget, here we actually need to still distribute our r to that because it comes along. And so at the end, like say we multiply this entire expression by r, That's going to give us, all right, so 20 minus 16 divided by 2. So that's 20 minus 8. That's going to be 12 minus, then we're going to have negative 5r squared plus 4r squared. So 20 minus r squared, and then minus r to the fourth over 2, and we're multiplying by r. So if we further simplify that, that's going to give us 12r minus r cubed minus r to the fifth over 2. And so that's what we want to use for our inner integral. So now we have an integral from 0 to 2 of 12r minus r cubed minus r to the fifth divided by 2 dr, which is going to be 6r squared minus r to the fourth over 4 minus r to the sixth divided by 12, evaluated from 0 to 2. So our bottom limits are going to give us, the zero limit is going to give us 0 for the entire expression. So again, we only need to worry about the 2. So 2 squared is 4, times 6 is 24, 2 to the fourth is 16, divided by 4 is 4, 2 to the sixth is 64, so minus 64 over 12, which is the same as what 4 divides into both of those, so we'll say that's 16 thirds instead. So minus 16 thirds, and what's that, 20, so 20 minus 16 thirds is the same as 60 minus 16 divided by 3, and that is 44 thirds. And so for our outer integral, we have from 0 to 2 pi of 44 thirds d theta, which is just 44 over 3 theta, evaluated from 0 to 2 pi, which is going to be 88 pi divided by 3. And if you wanted to go through the trouble, you could type this into Desmos and you get that answer. For example 2, so we have, all right, we're going to change some of the numbers so that it works out slightly easier. We're going to make this just 2 instead of the square root of 2. So that's going to be 2. We're going to make this 8 a 4. We'll cover up some stuff. So we'll make this 8, make that a 4. So make both of these 8s 4s instead. So that's going to be 4 minus x squared for both of those. So when you're coming up with your regions for integration, it's going to be helpful that you can draw like freehand this region. So let's see what's going on. The only, what makes the region is going to be our x's and our y's. The z is just going to be from -1 to 2. That's fine. But the x and y are going to dictate the region that we're integrating over. So the square root of 4 minus x squared is the upper part of a circle. Upper circle of our radius 2. And the negative square root of 4 minus x squared is the lower part of a circle. So what we have is, we'll say we have a circle of radius 2 in every direction. So this is what we have for y. Y is going from negative. So our y's are going from negative square root 4 minus x squared up to the positive square root 4 minus x squared. But our x's are going from 0 to 2. And that's the key part, because it limits our circle, which is going to limit our angle. So since x is going from 0 to 2, x is only on this region. So we only want this portion of the circle. That's where x is from 0 to 2. So we can just eliminate that part. And so what that's going to tell us is that our theta is from negative pi over 2 to positive pi over 2. And these angles aren't unique. We could also have this be, like, if we added 2 pi to both of those, it would be from 3 pi over 2 to 5 pi over 2. But as long as you have two angles that are consecutively making a half circle, um, that's going to work out. So if we rewrite our integral, so you know theta is from negative pi over 2 to positive pi over 2. R is from 0 to 2. And Z is the only one that generally never needs to change. And that's from -1 to 2. And that's because our height doesn't need to be parametrized in polar coordinates generally. So other than like converting the x and y's to like r squared or whatever. So when we write our integral, we're going to have the integral from negative pi over 2 to positive pi over 2, then an integral from 0 to 2, and then an integral from -1 to positive 2. And the square root of 1 plus x squared plus y squared is the same as the square root of 1 plus r squared. So we're going to have the square root of 1 plus r squared r dr d theta. I'm sorry, I forgot the dz. It's dz dr d theta. My apologies. So dz dr d theta. And since the first integral is for z, all of that is just a constant. And so when we integrate that, we're just going to get, we'll say r times 1 plus r squared to the 1/2 times z evaluated from -1 to 2 for the first integral. That's going to produce that. And since all we're doing is subtracting the value, so we have like 2 minus -1, which is just 3, we're going to get 3r times the square root of 1 plus r squared to the 1/2. So our middle integral is from 0 to 2 of 3r and 1 plus r squared to the positive 1/2 dr. And that's going to be a candidate for u substitution. So u is 1 plus r squared. Du is 2r dr. And we need to replace 3r dr. So if we multiply, all right, so we need to multiply both sides by 3/2 to end up with a 3r dr. So it's going to mean 3/2 du is equal to 3r dr. So our u limits are from, our r limits are from 0 to 2. Our u limits are going to be, if we substitute in 0, we're going to get 1. If we substitute in 2, we're going to get 1 plus 2 squared, which is 1 plus 4, which is 5. So we have the integral from 1 to 5 of 3/2 u to the 1/2 du. And when we integrate this, we're going to get 3/2 u to the 3/2 all divided by 3/2 or multiply by 2/3. And we want to evaluate from 1 to 5. So those 3/2 actually cancel out. And so we just get u to the 3/2. So that's going to give us 5 to the 3/2 minus 1 to the 3/2. And 5 to the 3/2 is the square root of 5 cubed. So that's going to be square root 5 times square root 5 times square root 5, which is really just 5 square root 5 minus 1 to the 3/2, which is 1. So that's the result for our middle integral. And then our outer integral is from negative pi over 2 to positive pi over 2 of 5 square root 5 minus 1 d theta, which is just 5 root 5 minus 1 theta evaluated from negative pi over 2 to positive pi over 2, which again, we're just subtracting these values. So pi over 2 minus negative pi over 2 is pi over 2 plus pi over 2, which is just pi. So we end up with pi times 5 square root 5 minus 1 as our final answer. So again, what this will represent is the mass of this object that has a variable density, and the density is just determined by this function. That's one way to interpret that. For example 3, these all kind of work the same. Just be aware of that. They all kind of function the same way. All right, so for example 3, maybe pause the video and see if you can come up with the integral in terms of x and y yourself. Remember, drawing a sketch is helpful. So, all right, so now, notice the order of integration. We have y, and then we have x. So what we have, if we draw this region, it's not gonna. So if we draw this region, we have the line y equals x, which is gonna just bisect quadrant 1. And so we're going from the line y equals x up to a circle of radius 1. So from y equals x to a circle of radius 1. So let's see. I didn't mean to do that. So let's draw a circle of radius 1. We'll make it a larger circle so you can see what's happening. So we're going from this line up to this circle. So our angle, so remember the limits are for y. So we're going from the line y equals x. So like y equals x. Remember in polar coordinates, that's going to be r cosine theta equals r, I'm sorry, I have this backwards. We'll say x equals y then. So r cosine theta equals r sine theta, which means that 1 is equal to the tangent of theta. And we know that means that pi over 4 is equal to theta. So we know our start angle is pi over 4. And the y's are moving from the line y equals x up to the circle, and our x's are moving from 0 to square root 2 over 2. So when we so if x is going in this, use a different color. Let's go to green. So if x is going from here, from 0 to square root 2 over 2, that means that obviously we're on a circle of radius 1, but our final angle is pi over 2 instead. So what we know is theta is, so we'll write over here, so theta is some angle that's between pi over 4 to pi over 2. R is from 0 to 1, and z is, so our z limits are last, so z is from 0 to 4, so z is from 0 to 4. So now when we rewrite our integral this time, so it's still theta comes last, so we have from pi over 4 to pi over 2. R is from 0 to 1. And again, we know it's a circle of radius 1 because it's just the square root of 1 minus x squared. And z is from 0 to 4. And we're going to have e to the negative r squared power, because x squared plus y squared is r squared. Then we have r dz dr d theta. Now, again, as long as the initial density function doesn't contain any z's, our first integral is just going to be the difference of our limits times this expression for r. So 4 minus 0 is 4. So for our inner integral, our middle integral, we really just want to evaluate from 0 to 1 of 4r e to the negative r squared dr power, dr. So use substitution again. U is going to equal negative r squared. Du is going to equal negative 2r dr. And what we need is a positive 4r. We need a positive 4r dr. So that would mean that negative 2 du is 4r dr. U limits are R limits are from 0 to 1. U limits are from 0 to 1 squared times -1, so -1. So we're going to have an integral from 0 to -1 of -2 e to the u du. And this is a straightforward integral. That's -2 e to the u evaluated from 0 to -1, which is -2 e to the -1 minus -2 e to the 0. So that's -2 over e plus 2. And then our final integral is from pi over 4 to pi over 2 times 2 minus 2 over e d theta. And again, this doesn't depend on theta, so our answer is going to be the difference of our limits times this constant. So we have 2 minus 2 over e times pi over 2 minus pi over 4, which is just pi over 4. So our final answer is pi over 4 times 2 minus 2 over e. Again, you can throw this into a calculator, but that's what you're going to get. I mean, I guess we could go farther, but they all kind of work the same. If you're looking at my notes ahead of time, I did make this change to example 4. I copied and pasted some stuff and then reorder my limits. So this should be from 0 to 4, then from 0 to 1/2. The upper limit is the square root of 1 minus y squared, and it should be dx, dy, dz. But I don't want to make the video too long doing the same kinds of problems. So example 4 and example 5, they work the same way. They have the same general setup. Some recommended problems are here. I would recommend looking at those. But they all kind of work the same way. Anyway, so thanks for watching. See y'all in class.